Settle into your seat, expand this to full screen if you haven't already, and consider subscribing if you find value in what follows, because what we're about to explore will take us on a journey far longer and more sobering than most are prepared to undertake. We live in an era saturated with images of gleaming habitats on rust-colored plains, of humans in sleek suits planting flags on distant hills, of children born under alien skies who will never know Earth except as a blue dot in their night sky. Mars, we are told, is humanity's next frontier, our backup planet, the world that will save us from ourselves. The rhetoric is intoxicating. It speaks to something ancient in our nature, the same impulse that drove our ancestors across oceans and over mountain ranges, into deserts and onto ice sheets. But there is a difference, a profound and unbridgeable difference between the harshest place on Earth and the most benign location on Mars. And it is this difference, examined through the unforgiving lens of physics, biology, medicine, engineering, and evolutionary reality, that forms the foundation of what follows. This is not a story of what we wish were true. It is an accounting of what is true, drawn from the laws that govern matter and energy, life and death, human frailty, and the cold indifference of a planet that has never, in all its 4.5 billion years, harbored a single living cell. Let us begin not with Mars, but with Earth, because only by understanding what makes our world uniquely suited to complex multicellular life can we grasp the magnitude of what Mars lacks. Earth is not merely a planet with water and a breathable atmosphere. It is the product of an extraordinarily specific set of initial conditions, cosmic accidents, and evolutionary feedbacks that have, over eons, created a self-regulating system of interlocking cycles. Our atmosphere is not a static shell, but a living product, generated and maintained by biology itself. The oxygen we breathe, comprising roughly 21% of the air, exists only because photosynthetic organisms have been exhaling it for billions of years. Before the Great Oxygenation Event approximately 2.4 billion years ago, Earth's atmosphere was anoxic, composed primarily of nitrogen, carbon dioxide, methane, and water vapor. The rise of oxygen was itself a catastrophe for much of the anaerobic life that had evolved in that earlier world, a mass extinction event that paved the way for aerobic metabolism and eventually for creatures like us, whose cells are powered by mitochondria that burn oxygen to extract energy from food with remarkable efficiency. This atmosphere is held in place by Earth's gravity, which is strong enough, given our planet's mass and radius, to retain even the lightest gases over geological timescales, while simultaneously allowing heavier volatiles to cycle through the crust and mantle via plate tectonics. Our magnetic field, generated by the convective motion of molten iron and nickel in the outer core, extends tens of thousands of kilometers into space, deflecting the charged particles of the solar wind and preventing them from stripping away our atmosphere, as happened long ago on Mars. The temperature at Earth's surface, averaging around 15 degrees Celsius, is maintained within a narrow habitable range by the greenhouse effect of water vapor, carbon dioxide, and other trace gases, a balance exquisitely tuned by feedbacks involving ocean chemistry, volcanic outgassing, and the silicate weathering cycle. Liquid water, that most ordinary of substances is stable across most of the planet's surface, existing in vast interconnected oceans that cover 71% of the area, moderating temperature swings, distributing heat from equator to poles, and providing the medium in which the chemistry of life unfolds. The pressure at sea level, approximately 101 kilopascals or 1 atmosphere, is high enough that water remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at standard pressure, and this pressure is itself a consequence of the sheer mass of air above us, a column extending from the surface to the edge of space. Now consider Mars. It is a smaller world with a diameter roughly half that of Earth and a mass only about 11% as great. This difference in mass translates directly into weaker gravity, approximately 38% of Earth's surface gravity, which has profound implications for both atmosphere retention and human physiology. Mars lost its global magnetic field over 4 billion years ago, likely due to the cooling and solidification of its core, and without this protective shield, the solar wind has spent eons scouring away the atmosphere. What remains today is a wisp, a trace, a ghostly remnant with a surface pressure averaging around 600 pascals, less than 1% of Earth's sea level pressure. To put this in perspective, this is equivalent to the pressure at an altitude of about 35 kilometers above Earth's surface, well into the stratosphere, far above the Armstrong limit where water boils at human body temperature. At such pressures, liquid water cannot exist on the Martian surface under current conditions. Any liquid water exposed to the atmosphere would immediately begin to boil and sublimate, transitioning directly from solid ice to water vapor in most locations, or briefly existing as a transient liquid in the deepest basins during the warmest part of the day before evaporating. The composition of this thin atmosphere is roughly 95% carbon dioxide, with nitrogen at just under 3%, argon at 1.6%, and only trace amounts of oxygen around 0.13%, produced not by life, but by the photodissociation of carbon dioxide molecules in the upper atmosphere. There is no oxygen to breathe, no nitrogen in sufficient quantity to support the biochemistry that terrestrial life depends upon, and no pressure to keep your blood from boiling if your suit were to fail. Temperature is another formidable barrier. Mars orbits the Sun at an average distance of about 1.5 astronomical units, receiving roughly 43% of the solar energy per unit area that Earth receives. Its thin atmosphere provides virtually no insulation, meaning that surface temperatures swing wildly between day and night and between equator and poles. The average surface temperature is around minus 63 degrees Celsius, but this average conceals extremes. At the equator during summer, daytime temperatures might briefly reach a balmy 20 degrees Celsius in direct sunlight, but at night, they plummet to minus 73 degrees Celsius or lower. Near the poles, winter temperatures can drop below minus 125 degrees Celsius, cold enough that carbon dioxide itself freezes out of the atmosphere and falls as dry ice snow, forming seasonal polar caps that advance and retreat with the Martian seasons. These are not conditions in which liquid water, let alone unprotected human flesh, can survive. A human standing on the Martian surface without a pressure suit would face a sequence of catastrophic failures within seconds. The low pressure would cause the gases dissolved in the bloodstream to come out of solution, forming bubbles, a condition known as ebulism. The moisture on the tongue, in the eyes, and in the lungs would begin to boil. The lack of oxygen would cause unconsciousness within 15 seconds as the brain was starved of its fuel. The cold, depending on the time of day and season, would begin to freeze exposed tissues within minutes. Death would follow swiftly, not from any single cause, but from the simultaneous assault of vacuum, hypoxia, and hypothermia. Mars, for all its superficial resemblance to Earth's deserts, is not a desert. It is a frozen, airless, irradiated wasteland, and no amount of optimism or technological aspiration changes this fundamental reality. Radiation is perhaps the most insidious and least visible of Mars's threats. On Earth, we are protected from the sun's ultraviolet radiation by the ozone layer, a thin stratum of triatomic oxygen molecules in the stratosphere that absorbs the most damaging wavelengths. We are protected from cosmic rays, high-energy particles originating from supernovae and other violent events across the galaxy, by our magnetic field and by the sheer mass of the atmosphere above us. On Mars, there is no ozone layer, no magnetic field, and almost no atmosphere. The surface is bathed in ultraviolet radiation at intensities that would cause severe sunburn and DNA damage within minutes. More troubling still is the ionizing radiation from cosmic rays and solar energetic particles. Cosmic rays are protons and atomic nuclei accelerated to near light speed, carrying energy so high that they can penetrate meters of rock and ice. When they strike the Martian surface or a human body, they interact with atomic nuclei, producing showers of secondary particles, including neutrons, which are themselves highly penetrating and biologically damaging. The radiation dose on the Martian surface is estimated at roughly 200 to 300 millisieverts per year, about 20 times the average annual dose received by a person on Earth at sea level, and well above the occupational limits set for radiation workers in most countries. Over the course of a year, a human on Mars would accumulate enough radiation to significantly increase lifetime cancer risk. Over a decade, the cumulative dose would virtually guarantee cancer in many tissues, particularly those with high cell turnover rates, such as the gastrointestinal tract and bone marrow. For a child growing up on Mars whose cells are dividing rapidly during development, the risk would be even greater. And this is assuming the colonists live in shielded habitats and venture outside only when necessary. Any prolonged surface activity, any attempt to farm or mine, or build infrastructure under the open sky would expose workers to doses that are frankly incompatible with long-term health. Let us turn now to gravity, because the effects of reduced gravity on the human body are neither subtle nor easily mitigated. We know this from decades of research aboard the International Space Station and earlier space stations, where astronauts have lived in microgravity for months at a time. The human body, it turns out, is exquisitely adapted to the one-gravity environment of Earth. Our bones are not static structures, but dynamic tissues, constantly being remodeled by cells called osteoblasts, which build bone, and osteoclasts, which break it down. This remodeling is regulated by mechanical stress. When you walk, run, or simply stand, the weight of your body compresses your skeleton, and this compression signals osteoblasts to lay down new bone. In microgravity, this mechanical stress vanishes and the balance shifts. Osteoclasts continue to resorb bone, but osteoblasts reduce their activity. The result is rapid bone loss, on the order of 1 to 2% of bone mass per month in the weight-bearing bones of the legs and spine. Astronauts returning from 6-month missions have lost up to 20% of their bone density in some skeletal sites, equivalent to decades of age-related osteoporosis compressed into half a year. On Mars, with its 38% gravity, the situation is less extreme than in microgravity, but still deeply concerning. The mechanical loading on bones would be roughly a third of what evolution has tuned our skeletons to expect. Would this be enough to prevent bone loss? We do not know, because no human has ever lived in partial gravity for an extended period. Animal studies suggest that partial gravity may slow, but not eliminate bone loss, and that there may be a threshold below which the skeletal system cannot maintain homeostasis. If Martian gravity is below this threshold, colonists would face progressive skeletal degradation, increasing fracture risk, and the potential for debilitating osteoporosis by middle age. Muscle atrophy is another consequence of reduced gravity. Muscles, like bones, adapt to the demands placed upon them. In microgravity, astronauts can lose up to 20% of muscle mass over the course of several months, particularly in the legs and lower back, because these muscles are no longer needed to support body weight against gravity. Astronauts on the ISS exercise for 2 hours a day, 6 days a week, using resistance machines and treadmills, and even with this rigorous regimen, they still lose muscle and bone. On Mars, colonists would need to exercise constantly just to slow the deterioration of their musculoskeletal system, and it is unclear whether any amount of exercise in 38% gravity can fully compensate for the absence of Earth normal loading. Then there is the cardiovascular system. On Earth, the heart must pump blood upward against gravity to supply the brain and upper body, and this provides a constant workout for the cardiac muscle. In microgravity, the heart does not have to work as hard, and it atrophies, becoming smaller and weaker. Astronauts returning from space often experience orthostatic intolerance, a condition in which standing up causes blood to pool in the legs, leading to dizziness, fainting, and an inability to maintain blood pressure. On Mars, the reduced gravity would place less demand on the cardiovascular system than Earth does, but more than microgravity. And again, we do not know where the threshold lies. Would the heart of a Martian colonist, after years in 38% gravity, be capable of functioning normally if that person were ever to return to Earth? The answer is almost certainly no. The physiological adaptations to Martian gravity would likely be irreversible, or at least extremely difficult to reverse, meaning that anyone who spends years on Mars would become physiologically incapable of living on Earth. They would be exiles, cut off not by distance alone, but by the very biology of their bodies. The effects extend to the inner ear, to the vestibular system that governs balance and spatial orientation. Astronauts in microgravity often experience space motion sickness, a profound disorientation caused by the conflicting signals from the eyes, the vestibular system, and proprioceptors in the muscles and joints. This typically resolves after a few days as the brain adapts, but the adaptation itself is a problem when returning to gravity. Astronauts landing back on Earth often feel heavy, clumsy, and disoriented for days or weeks. On Mars, the vestibular system would have to adapt to a gravity field that is neither Earth normal nor zero, and it is unclear how well this adaptation would proceed or what long-term effects it might have on balance, coordination, and spatial cognition. There's also the issue of fluid shifts. On Earth, gravity pulls blood and other bodily fluids toward the legs. When you lie down, fluids redistribute toward the head and upper body, which is why you might feel congested in the morning. In microgravity, fluids shift headward permanently, causing puffy faces, congested sinuses, and a phenomenon known as spaceflight-associated neuroocular syndrome, or SANS, in which the increased intracranial pressure flattens the eyeball, causing changes in vision that can persist long after return to Earth. Some astronauts have experienced permanent degradation of visual acuity. On Mars, fluid shifts will be less pronounced than in microgravity, but still present to some degree, and the long-term consequences are unknown. The human body, in short, is not modular. It is not a machine that can be tuned to operate in any environment. It is a product of 4 billion years of evolution in a one-gravity, oxygen-rich, temperate, wet environment, and every system, from the cellular to the organismal, reflects this history. Consider the immune system. There's growing evidence that spaceflight, even short-duration missions, can impair immune function. Astronauts are more susceptible to viral reactivation, particularly of latent herpes viruses like varicella zoster, the virus that causes chickenpox and shingles. They show altered patterns of gene expression in immune cells, reduced activity of natural killer cells, and slower wound healing. The mechanisms are not fully understood, but they likely involve the combined stresses of radiation, altered gravity, isolation, confinement, and disrupted circadian rhythms. On Mars, these stresses would be chronic, not acute. Colonists would live their entire lives in a low-gravity, high-radiation environment, isolated from Earth, confined to pressurized habitats, and subjected to psychological stresses we will explore shortly. Their immune systems, compromised and overstressed, would be less capable of fighting off infections, and any infection in a small isolated colony could spread rapidly. There would be no hospitals, no intensive care units, no specialists in infectious disease or trauma surgery. Medical care would be limited to what can be provided by the small number of people on site, using equipment and pharmaceuticals transported from Earth at enormous cost. A simple appendicitis, easily treatable on Earth, could become a death sentence on Mars if complications arise. A fracture could lead to chronic disability if it heals poorly in low gravity. A cancer caused by accumulated radiation exposure might be untreatable without access to advanced chemotherapy, radiation therapy, or surgical oncology. And then there is reproduction. If Mars is to be a true colony, not merely a research outpost, then children must be born there. But can humans reproduce in Martian gravity? We do not know. No mammal has ever conceived, gestated, and given birth in reduced gravity. Studies in microgravity using rodents aboard spacecraft have shown that embryonic development is disrupted with increased rates of abnormality and failure. Some fish and amphibians can reproduce in microgravity, but mammals, with their more complex developmental pathways and longer gestation periods, face greater challenges. Gestation in humans involves a delicate choreography of hormonal signals, immune tolerance, placental development, and fetal growth, all occurring in a one-gravity environment. The placenta must establish a robust blood supply to nourish the fetus, and this involves the invasion of maternal spiral arteries by fetal trophoblast cells, a process that might be disrupted by altered gravity. The fetus itself, floating in amniotic fluid, experiences the pull of gravity, which may influence the development of the musculoskeletal system, the cardiovascular system, and the vestibular system. A fetus developing in Martian gravity would experience less mechanical loading on its developing bones and muscles, potentially resulting in weaker structures. It might fail to develop the cardiovascular adaptations necessary to function in Earth normal gravity, becoming from birth a true Martian, incapable of ever leaving the planet. And what of the birth itself? Human childbirth is already a risky process, one of the most dangerous events a woman can undergo, because the size of the human head relative to the birth canal is marginal, a consequence of our bipedalism and large brains. In reduced gravity, the mechanics of labor might be altered, potentially complicating delivery. If complications arise, a cesarean section, a major abdominal surgery requiring anesthesia, sterile technique, and post-operative care would have to be performed in a habitat with limited medical resources. The maternal mortality rate on Mars could be staggering. Even if birth succeeds, the child faces a lifetime of challenges. Infant development on Earth involves constant interaction with gravity. Babies learn to lift their heads, to sit, to crawl, to stand, and to walk, each milestone requiring ever greater strength and coordination in a one-gravity field. On Mars, these milestones would be reached in a different gravitational environment, and the resulting motor patterns might be fundamentally different. A child who learns to walk in Martian gravity would develop a gait adapted to that environment, with different patterns of muscle activation, different joint loading, and different proprioceptive feedback. If that child were ever brought to Earth, they might find it impossible to walk normally, or even to stand for extended periods. Their bones, never subjected to full Earth gravity during their critical years of growth, might be fragile and prone to fracture. Their heart, adapted to pumping blood in a low-gravity environment, might be incapable of maintaining adequate circulation in one gravity. And their psychology, shaped by a childhood lived entirely indoors, in a confined habitat under a sky that is never blue, in a world where going outside requires a spacesuit and where every resource is scarce and recycled, would be unlike anything we have seen on Earth. What would it mean for a child to grow up knowing that they can never, ever set foot on the planet where their species evolved, where billions of their fellow humans live, where the air is free and the oceans vast and the forests teem with life? What would it do to the human psyche to be born into exile? Let us consider the habitat itself, because a Martian colony would not be a settlement in any traditional sense. It would be a sealed, pressurized life support system, more akin to a submarine or a space station than to a town or village. Every habitat module would have to maintain an internal pressure of roughly 1 atmosphere, requiring walls strong enough to withstand the pressure differential between inside and outside. These walls would also need to provide radiation shielding, which means either burying the habitat under several meters of Martian regolith or constructing walls of immense thickness using water, polyethylene, or other hydrogen-rich materials. The habitat would need airlocks for entry and exit, and these airlocks would be points of vulnerability, places where seals can fail and leaks can occur. The interior atmosphere would have to be carefully managed, with oxygen produced from Martian resources or imported from Earth, carbon dioxide scrubbed from the air by chemical or biological means, and humidity, temperature, and pressure continuously monitored and adjusted. Any failure of the life support system, any breach in the hull, any contamination of the air supply would be catastrophic. The colonists would be living on a knife edge where a single equipment failure could kill everyone in the habitat within minutes or hours. Power is another fundamental constraint. On Earth, we take energy for granted. We have abundant fossil fuels, hydroelectric dams, nuclear power plants, and increasingly solar and wind farms. Energy is cheap, available, and reliable. On Mars, every watt of power must be generated locally because there is no grid, no infrastructure, no supply chain. Solar power is less efficient on Mars than on Earth because Mars receives less sunlight, and because dust storms can block the sun for weeks at a time. Solar panels would need to be large, and they would require regular cleaning to remove the fine dust that settles on them, a task that is straightforward on Earth, but dangerous and labor-intensive on Mars, where every extravehicular activity carries risk. Nuclear power is a more reliable option, using small modular reactors or radioisotope thermoelectric generators, but these come with their own challenges. Reactor fuel must be brought from Earth, and the reactor itself must be shielded and maintained, requiring skilled personnel and specialized tools. Any malfunction could release radiation, contaminating the habitat and surrounding area. And even with a reliable power source, the energy budget on Mars would be tight. Power would be needed for life support, for heating the habitat against the cold Martian night, for running computers and communication equipment, for manufacturing and repair, for growing food, for processing water and producing oxygen, and for charging the batteries of rovers and spacesuits. Every activity would be energy constrained, and efficiency would be paramount. Water, that most essential of substances, would be scarce. Mars has water locked up as ice in the polar caps and buried beneath the surface at higher latitudes, but extracting and purifying it would require energy and equipment. The water ice would have to be excavated or drilled, melted, filtered to remove salts and perchlorates, and then sterilized to ensure it is free of any potential Martian microbes, should they exist. This water would then have to be recycled with near-perfect efficiency because bringing water from Earth is prohibitively expensive. Every drop of water used by a colonist for drinking, cooking, washing, or growing food would have to be reclaimed from wastewater, purified, and reused. The recycling systems would be complex, involving filtration, distillation, chemical treatment, and biological processing, and any failure in these systems would lead to water shortages, which in a closed-loop habitat would quickly become life-threatening. The same is true for food. A Martian colony cannot be supplied indefinitely from Earth because the cost of launching mass to Mars is measured in thousands of dollars per kilogram. The colonists would need to grow their own food using controlled environment agriculture in pressurized greenhouses. But growing food on Mars is not as simple as planting seeds in Martian soil. The regolith, though it contains many of the elements needed for plant growth, is also contaminated with perchlorates, toxic salts that would have to be removed before the regolith could be used as a growth medium. The soil would need to be supplemented with organic matter, nitrogen-fixing bacteria, and other soil microorganisms, creating a living soil ecosystem from scratch. The plants would need light, either from the sun, filtered through transparent greenhouse panels, or from artificial lights powered by the habitat's energy supply. They would need water, nutrients, carbon dioxide, and careful temperature control. The entire agricultural system would be fragile, vulnerable to pests, diseases, equipment failures, and human error. A single blight, a single pest introduction, a single miscalculation in nutrient balance could destroy an entire crop, leading to famine. And even if food production succeeds, the diet on Mars would be monotonous and nutritionally precarious. The colonists would be eating whatever crops can be grown most efficiently in a closed system, likely a limited palette of staples such as potatoes, wheat, rice, soybeans, leafy greens, and perhaps some vegetables and fruits. There would be little variety, no fresh meat, no fish, No dairy unless the colony goes to the extraordinary lengths of raising animals, which would require even more space, water, food, and energy. The psychological impact of such a diet, month after month, year after year, should not be underestimated. On Earth, food is not merely fuel. It is culture, tradition, pleasure, and comfort. Meals are social events, times of connection and celebration. On Mars, food would be functional, a source of calories and nutrients, but stripped of much of what makes eating a human experience. The monotony, the lack of fresh ingredients, the absence of the foods one grew up with would contribute to a sense of deprivation and alienation, compounding the other psychological stresses of Martian life. Speaking of psychology, let us delve into the mental and emotional challenges of living on Mars, because these may be as formidable as the physical challenges and far less amenable to technological solutions. Humans are social creatures, evolved to live in groups, to form bonds, to communicate, to cooperate, and to compete. We are also creatures of the outdoors, adapted to a world of vast horizons, changing weather, natural light, and sensory richness. A Martian colony would be the antithesis of this. It would be a confined space populated by a small number of individuals, perhaps a few dozen or at most a few hundred in the early stages, with no opportunity for privacy, no escape from one another, and no contact with the natural world except through the narrow windows of a spacesuit helmet. The psychological stresses of such an environment are well documented from analog studies conducted in Antarctica, in isolated research stations, and in submarine crews. These environments produce what is known as the third quarter phenomenon, a psychological slump that occurs roughly 3/4 of the way through a long-duration mission, characterized by depression, irritability, insomnia, and interpersonal conflict. In extreme cases, individuals experience cabin fever, a state of restless agitation and emotional instability caused by prolonged confinement. On Mars, these effects would be amplified by the knowledge that there is no early escape, no possibility of returning home if things become unbearable, and by the constant awareness of the hostile environment just beyond the habitat walls. Isolation from Earth would be profound. Communication with Earth would be delayed by the light travel time, which ranges from about 3 minutes when Mars is at its closest to Earth, to over 20 minutes when the two planets are on opposite sides of the Sun. This means that conversations cannot be real time. Every message sent from Mars would be met with silence for at least 6 minutes and often much longer, making it impossible to have a natural back and forth dialogue. Phone calls with loved ones would be replaced by asynchronous exchanges of recorded messages, lacking the immediacy, the emotional nuance, the give and take of conversation. This communication lag would foster a sense of disconnection, of being cut off from humanity, of living in a bubble divorced from the ongoing life of the civilization that sent you. News from Earth would be old by the time it arrived, and the colonists would have no ability to participate in real-time events, whether personal milestones, political crises, or cultural moments. They would be spectators watching the life of Earth from a distance, unable to touch it or be touched by it. The visual environment of Mars would be alien and oppressive. The sky, instead of being blue, would be a butterscotch hue during the day, caused by the scattering of sunlight by the fine dust suspended in the thin atmosphere. At sunset, the sky near the sun would take on a bluish tint, the inverse of Earth's red sunsets, a small but psychologically jarring reminder that this is not home. The landscape, though possessed of a stark beauty, is monotonous, dominated by rocks, sand, and dust, with no vegetation, no water, no movement except the occasional dust devil or the slow advance of sand dunes. There are no birds, no insects, no animals, no sounds except the hiss of air in your suit and the crunch of regolith under your boots. The silence is absolute. On Earth, even in the quietest places, there is ambient noise, the rustle of leaves, the distant sound of water, the hum of insects, the calls of birds. On Mars, outside the habitat, there is nothing, a silence so profound it becomes a presence in itself, pressing in on the mind. And the stars, though unobscured by light pollution and visible in far greater numbers than from most places on Earth, would be cold comfort, a reminder of the immense emptiness of space and the fragility of the tiny bubble of life that is the habitat. Inside the habitat, life would be governed by routine and necessity. Every day would be structured around work, maintenance, exercise, meals, and sleep. There would be little leisure, little time for pursuits that are not directly related to survival. The colonists would be engineers, technicians, scientists, doctors, and farmers, multitasking across roles because there are not enough people to specialize. They would be constantly busy, troubleshooting problems, repairing equipment, monitoring systems, conducting experiments, and preparing for the next challenge. Boredom, paradoxically, would coexist with overwork, because while the tasks are demanding, they are also repetitive, and the environment offers no novelty, no surprise, no opportunity for spontaneous adventure or exploration beyond the carefully planned and resource-limited extravehicular activities. Relationships within the colony would be intense and fraught. In a small isolated group, personalities clash, grievances accumulate, and there is no escape from the people you dislike. On Earth, if you have a conflict with a coworker or neighbor, you can leave. You can go home. You can find other social circles. On Mars, you are stuck with the same few dozen people day after day, month after month, year after year. The potential for interpersonal conflict, factionalism, and even violence is significant, and managing these dynamics would require extraordinary emotional intelligence, maturity, and conflict resolution skills. The colony would need strong leadership, clear rules, and mechanisms for addressing disputes, but even with these, the stresses of the environment would inevitably lead to psychological casualties. Depression, anxiety, and post-traumatic stress would be common. The rate of mental illness in such an environment would almost certainly be higher than in the general population on Earth, and treating mental illness on Mars would be difficult. There would be no psychiatric hospitals, no therapists except perhaps through telemedicine with Earth, subject to the communication delays that make real therapy impossible. Medications would be limited to what can be stocked or synthesized on site, and the long-term effects of these medications in a low-gravity, high-radiation environment are unknown. Suicide would be a risk, perhaps the greatest risk, because a person who decides they cannot continue living on Mars has no options, no way to leave, no place to go. The psychological burden of knowing that you are trapped, that you have made an irrevocable choice to spend the rest of your life in a hostile, confined environment, far from everyone and everything you knew, would be crushing for many people. And if someone does decide to end their life, the impact on the rest of the colony would be devastating, undermining morale, sowing doubt, and potentially triggering a cascade of further psychological crises. Now let us turn to the question of governance and social structure, because a Martian colony would not merely be a technical challenge, but a social and political one. Who would govern Mars? By what laws would the colonists live? Who would own the land, the resources, the means of production? These are not abstract questions. They are practical matters that would have to be resolved before any colony is established, and the answers would shape the character of Martian society. If the colony is funded and operated by a private corporation, as many current proposals envision, then the colonists would effectively be employees, subject to corporate rules and corporate interests. They would have little autonomy, little say in how the colony is run, and little recourse if they disagree with management decisions. The company would own the habitats, the equipment, the means of survival, and could in theory withhold these to enforce compliance. This is a recipe for exploitation for a dystopian company town in space where workers have no rights and no alternatives. If, on the other hand, the colony is established as a democratic polity with laws and governance structures agreed upon by the colonists, then questions of jurisdiction, sovereignty, and accountability arise. Would Mars be subject to Earth laws, perhaps under the framework of the Outer Space Treaty, which declares celestial bodies to be the common heritage of humanity and forbids national appropriation? Or would Mars declare independence, establishing its own legal system and government? And if the latter, how would Earth respond? History suggests that colonies often seek independence from their mother countries, and that such independence movements can be peaceful or violent, depending on the circumstances. A Martian colony, once established, might well develop interests that diverge from those of Earth, and conflicts could arise over resources, trade, governance, and autonomy. But unlike earthly colonies, Mars cannot be easily reached or controlled by Earth. The distances are too great, the travel times too long, and the costs too high for Earth to exert direct military or political control over Mars. Mars would be de facto independent from the outset, whether Earth recognizes it or not, and this independence would be both a freedom and a curse, because it means that the colonists would be entirely responsible for their own survival, with no guarantee of assistance from Earth if things go wrong. The economics of a Martian colony are deeply problematic. Colonies on Earth historically were established for economic reasons, to extract resources, to establish trade routes, to claim land for agriculture. But what economic activity could sustain a Martian colony? Mars has no resources that Earth needs and cannot obtain more cheaply elsewhere. There's water, but Earth has plenty of water. There are minerals, but asteroid mining would be far more cost-effective than mining on Mars, because asteroids lack a gravity well and require less energy to escape. There's no breathable atmosphere to harvest, no biosphere to exploit, no indigenous population to trade with or subjugate. The only thing Mars has is land, and land on Mars is worthless because it cannot support human life without massive technological infrastructure. Some have suggested that Mars could export knowledge, that it could be a center of scientific research, generating discoveries and innovations that Earth would pay for. But this is implausible. Any research that can be done on Mars can be done on Earth or in Earth orbit at a fraction of the cost and risk. The only research that is unique to Mars is research on Mars itself, studying its geology, its climate, its potential for past life. And this research can be done more effectively and safely by robotic probes than by human scientists. Others have suggested that Mars could become a hub for further space exploration, a staging ground for missions to the outer solar system or beyond. But this too is economically dubious. Launching from Mars is easier than launching from Earth due to the lower gravity and thinner atmosphere, but you still have to get all the equipment and fuel to Mars in the first place, which negates the advantage. It is more efficient to launch deep space missions from Earth orbit or from the Moon, which is much closer and has even lower gravity than Mars. The inescapable conclusion is that a Martian colony would be a perpetual money pit, requiring continuous subsidies from Earth to pay for supplies, equipment, and the transport of personnel. It would be, in economic terms, a vanity project, a demonstration of technological prowess with no hope of ever becoming self-sustaining or profitable. The only entities capable of funding such a project are governments driven by geopolitical prestige or scientific curiosity, or billionaires driven by personal obsession or a desire for a legacy. And history shows that such projects, when they lose political support, or when the benefactor loses interest or resources, are abandoned. The colonists would be left stranded, unable to return to Earth, unable to maintain their equipment without supplies from Earth, facing a slow collapse of their life support systems and an inevitable decline into starvation, asphyxiation, or some other form of systems failure. This is not speculation. It is the logical endpoint of a colony that has no economic foundation and depends entirely on the goodwill and resources of a distant patron. Let us consider the timescales involved in establishing even a minimal colony. Getting to Mars is not a quick trip. Launch windows, when Earth and Mars are favorably aligned, occur roughly every 26 months, and the journey itself takes between 6 and 9 months, depending on the trajectory and the propulsion system used. This means that any resupply mission from Earth would take at least 2 years from the decision to send it to its arrival on Mars, including the wait for the next launch window and the transit time. If something goes wrong on Mars, if there is an equipment failure or a medical emergency or a crop failure, the colonists would have to survive on their own for at least 2 years before help could arrive, assuming that Earth even sends help, and assuming that the help arrives in time. In practice, the colonists would need to be entirely self-sufficient, because relying on resupply from Earth is too slow and too uncertain. But achieving self-sufficiency would require manufacturing capabilities that are far beyond anything we have demonstrated. The colony would need to produce its own oxygen, water, food, spare parts, electronics, chemicals, pharmaceuticals, and construction materials. It would need machine shops, chemical plants, greenhouses, mining equipment, smelters, and fabrication facilities. It would need a large and skilled workforce, trained in a wide array of disciplines, from mechanical engineering to organic chemistry to medicine to agronomy. Building up this infrastructure would take decades, not years, and would require enormous quantities of equipment and materials transported from Earth at the outset. The cost would be measured in the hundreds of billions or even trillions of dollars, dwarfing any civilian infrastructure project ever undertaken on Earth. And then there is the question of return. Can colonists return to Earth if they choose to leave Mars, or if they must leave due to medical or personal reasons? In principle, yes, but in practice, the challenges are severe. A return mission would require a spacecraft capable of launching from the Martian surface, ascending to orbit, performing a trans-Earth injection burn, surviving the months-long journey back, and then decelerating for re-entry into Earth's atmosphere. This spacecraft would need fuel, which would have to be produced on Mars or brought from Earth, and it would need to be maintained and ready to launch at any time, which is difficult in the harsh Martian environment. More troubling is the physiological challenge of returning to Earth after years in Martian gravity. As we've discussed, the human body adapts to the local gravity environment, and these adaptations will make return to Earth difficult and possibly dangerous. Colonists who have lived on Mars for many years might find that their bones are too weak to support their weight in Earth gravity, that their muscles are too atrophied to walk, that their cardiovascular system cannot maintain adequate blood pressure. They would require months of rehabilitation, possibly using centrifuges to gradually readapt to higher gravity, and even then, full recovery might not be possible. For practical purposes, anyone who spends more than a few years on Mars would be unable to return to Earth, making the decision to go to Mars a one-way trip, a permanent exile. Now let us examine some of the more speculative proposals for making Mars habitable, because these are often invoked as solutions to the problems we've been discussing. The most ambitious of these is terraforming, the idea of transforming Mars into an Earth-like planet with a breathable atmosphere, liquid water on the surface, and temperatures suitable for unprotected human habitation. Terraforming Mars would require thickening the atmosphere to increase pressure and temperature, introducing greenhouse gases to warm the planet, releasing oxygen into the air, and perhaps even engineering a magnetic field to protect the new atmosphere from the solar wind. The challenges are staggering. Mars has lost most of its original atmosphere over geological time, and simply releasing the carbon dioxide locked in the polar caps and in the regolith would not be enough to create a breathable atmosphere. Studies suggest that even if all of the accessible carbon dioxide on Mars were released, the resulting atmospheric pressure would still be far below Earth's, perhaps only a few percent, not nearly enough for liquid water to be stable or for humans to breathe. To create an Earth-like atmosphere, you would need to import volatiles from elsewhere, perhaps by redirecting comets or asteroids rich in water and nitrogen to impact Mars. But this would require technologies and energies that are entirely beyond our current capabilities, and the risks of such a project, including the possibility of uncontrolled impacts that devastate the surface, are immense. Even if you could thicken the atmosphere, you would need to warm the planet, which would require a sustained greenhouse effect. Some have proposed using perfluorocarbons, extremely potent greenhouse gases, to trap heat, but producing these gases in the quantities needed would require industrial infrastructure on a scale that does not exist on Mars and would take centuries to build. Others have proposed using orbital mirrors to concentrate sunlight on the polar caps, melting them and releasing carbon dioxide. But again, the scale of such mirrors would be enormous, and the energy required to place them in orbit and maintain them would be prohibitive. And even if you succeeded in warming Mars and thickening the atmosphere, you would still need to produce oxygen. Photosynthesis by genetically engineered plants or cyanobacteria is the most plausible mechanism, but it would take millennia for biological processes to convert a carbon dioxide atmosphere into an oxygen-rich one, assuming that the organisms could even survive the high radiation levels and the harsh conditions. The timescales for terraforming Mars, if it is even possible, are measured in thousands to tens of thousands of years, making it irrelevant to any discussion of near-term or even medium-term colonization. Another proposal is to live in lava tubes, natural tunnels formed by ancient volcanic activity, which exist in large numbers on Mars. Lava tubes would provide natural radiation shielding and some protection from temperature extremes, and they would be easier to seal and pressurize than surface habitats. This is a more practical idea than terraforming, but it comes with its own challenges. Lava tubes would need to be explored and mapped, which is difficult and dangerous. They might be structurally unstable, prone to collapse, especially given Mars's seismic activity and the weakness of its crust. They would need to be cleaned, leveled, and fitted with airlocks, life support systems, and all the other infrastructure of a habitat. And living in a lava tube would mean living underground, in perpetual darkness, with no natural light, no views of the surface, no connection to the sky. The psychological effects of such an environment would be severe, compounding the already significant mental health challenges of life on Mars. Some people might adapt, but many would not, and the colony would be selecting for a very specific personality type, one that can tolerate confinement, darkness, and isolation for extended periods. Let us compare Mars to other extreme environments on Earth where humans have attempted to live, because these comparisons are instructive. Antarctica is often cited as an analog for Mars, and there are indeed similarities. Antarctica is cold, dry, isolated, and inhospitable, but Antarctica is paradise compared to Mars. Antarctica has a breathable atmosphere. It has liquid water, albeit frozen most of the time. It has wildlife, including penguins, seals, and whales in the surrounding oceans. It has seasons, with the sun rising and setting in cycles, even if those cycles are extreme. It has a magnetosphere protecting it from radiation. It has gravity that is exactly one Earth gravity. And despite all these advantages, permanent human settlement in Antarctica is essentially non-existent. The research stations are inhabited only during the summer months or year-round by rotating crews who stay for a limited time and then leave. No one lives their entire life in Antarctica. No one raises families there. No one has built a self-sustaining community. The cost and difficulty of maintaining even these temporary research stations is enormous, requiring constant resupply by ship and aircraft. If humans have not permanently colonized Antarctica, a place that is far more hospitable than Mars, what reason is there to believe that Mars can be colonized? Consider also the history of human settlement in other marginal environments: the high Arctic, the deep deserts, the high mountains. Humans have lived in these places, but only in small numbers, and only with difficulty. The Inuit of the Arctic live by hunting and fishing, exploiting the sparse but present biosphere. The Bedouin of the deserts lived by herding animals and trading, moving from oasis to oasis. The Sherpa of the Himalayas live by farming in the valleys and serving as guides and porters for expeditions. All of these communities relied on resources provided by the earth, by the biosphere, by the cycles of life that make our planet habitable. None of them lived in environments that were as hostile as Mars, and none of them could have survived without the broader human civilization to trade with, to draw resources from, to provide a safety net. Isolated communities that have tried to cut themselves off from civilization, whether for religious, political, or ideological reasons, have generally failed. They run out of resources, suffer from inbreeding and genetic bottlenecks, fall victim to disease or disaster, or simply collapse from internal social tensions. A Martian colony would face all of these challenges. amplified by the fact that the environment itself is actively trying to kill you. Let us think about genetic diversity, because this is a concern that is often overlooked in discussions of colonization. A viable population needs genetic diversity to avoid inbreeding and to maintain the genetic variation necessary for adaptation and resilience. Population geneticists have estimated that a minimum effective population size for long-term survival, avoiding inbreeding depression and maintaining genetic health, is on the order of several thousand individuals and possibly as high as 10,000. A Martian colony in its early stages would be far smaller, perhaps a few dozen to a few hundred people. These individuals would be selected from a narrow pool, likely skewed towards certain demographics, certain skill sets, certain geographic and ethnic origins. The resulting population would have limited genetic diversity, and if the colony remains small and isolated, inbreeding would become a concern within a few generations. The effects of inbreeding include increased rates of genetic disorders, reduced fertility, and decreased overall fitness. Managing this would require careful genetic planning, perhaps using reproductive technologies such as in vitro fertilization with donor gametes, but this assumes a level of medical infrastructure and expertise that would be difficult to maintain on Mars. It also raises ethical questions about reproductive autonomy and the rights of individuals to choose their own partners and have their own children. Let us consider also the question of cultural and intellectual stagnation. Human civilization on Earth is characterized by immense diversity, by the constant exchange of ideas, by the collision and synthesis of different cultures, philosophies, technologies, and artistic traditions. This diversity is a source of creativity, innovation, and resilience. A small, isolated Martian colony would lack this diversity. The colonists would be drawn from a limited cultural pool, and the isolation from Earth would mean that new ideas, new art, new science from Earth would reach them only with delays and through the filter of whatever communication infrastructure exists. Over time, Martian culture would diverge from Earth culture, but it would be a divergence born of isolation and limitation, not of richness and innovation. The colony might develop its own traditions, its own social norms, its own identity, but these would be shaped by the constraints of the environment and the smallness of the population. There would be little room for dissent, little room for alternative lifestyles, little room for the kind of experimentation and exploration that characterizes human culture at its best. The colony would be conformist, conservative, focused on survival rather than flourishing. Intellectual life would be impoverished because the resources for education, for research, for the arts and humanities would be limited. There would be no great libraries, no museums, no concert halls, no theaters. Entertainment would be limited to whatever can be produced locally or streamed from Earth with delays. Education would be functional, focused on the skills needed to maintain the colony, with little room for philosophy, literature, history, or the arts. The children of Mars would grow up in a world that is intellectually and culturally barren, and this would shape their thinking, their aspirations, their sense of what is possible. Let us turn now to the question of motivation. Why would anyone choose to go to Mars, knowing all of these challenges, all of these risks, all of these deprivations? The most common answer is idealism, the belief that humanity must become a multiplanetary species to ensure its long-term survival, that spreading to other worlds is our destiny, our purpose, the next step in our evolution. This is a compelling narrative, but it is also a form of magical thinking, a refusal to engage with the reality of what life on Mars would actually be like. The people who volunteer to go to Mars would be motivated by a complex mix of idealism, adventure-seeking, escapism, and perhaps a desire to be part of something historic. But motivation is not the same as suitability. The psychological profile of someone who wants to go to Mars might not be the same as the profile of someone who could actually thrive there. And once on Mars, the reality would set in. The adventure would fade, replaced by the grinding routine of survival. The idealism would be tested by the discomforts, the dangers, the isolation, the loss of everything familiar. Some people would adapt, others would regret their decision, but by then, it would be too late. They would be trapped, exiles on a world that does not want them, kept alive only by technology that could fail at any moment. There's also the question of ethics. Is it ethical to send people to Mars, knowing the risks, knowing the likelihood of failure, knowing that they might suffer and die? Is it ethical to bring children into such an environment? Children who did not choose to be born on Mars and who will bear the consequences of their parents' decision for their entire lives. Is it ethical to spend the immense resources required for a Martian colony when those resources could be used to address pressing problems on Earth? Problems such as poverty, disease, climate change, and environmental degradation. These are not easy questions, and they do not have clear answers, but they must be asked. The drive to explore, to push boundaries, to reach for the stars is deeply human, but so is the responsibility to act with wisdom, with caution, with consideration for the well-being of others. The history of exploration on Earth is filled with triumphs, but it is also filled with tragedies, with expeditions that ended in death, with colonies that collapsed, with indigenous peoples who were displaced or destroyed. We should learn from this history, not repeat it on a new world. Let us examine the track record of closed-loop life support systems, because a Martian colony would depend entirely on such systems. On Earth, we have attempted to build closed or semi-closed ecosystems in controlled environments, most famously in the Biosphere 2 project in Arizona. Biosphere 2 was a massive sealed structure containing multiple biomes, from rainforest to desert to ocean, with the goal of creating a self-sustaining ecosystem that could support a crew of 8 people for 2 years. The first mission from 1991 to 1993 encountered numerous problems. Oxygen levels dropped, requiring the injection of oxygen from outside, violating the closed system protocol. Carbon dioxide levels fluctuated wildly. Nitrous oxide, a byproduct of microbial activity in the soil, accumulated to toxic levels. Many of the plant and animal species introduced into Biosphere 2 died out. Ants and cockroaches thrived, outcompeting other species. The crew experienced hunger, as food production fell short of needs. They also experienced interpersonal conflict and psychological stress. The project was a partial failure, demonstrating that creating a stable, closed ecosystem is far more difficult than anticipated, even on Earth, where you can open a door and walk out if things go wrong. Mars would offer no such escape. A biosphere-type system on Mars would be smaller, less diverse, and subject to the additional stresses of low gravity, high radiation, and the need to produce all resources from local materials. The likelihood of long-term success is low. Another relevant example is the International Space Station, which has been continuously inhabited for over 2 decades, a remarkable achievement. But the ISS is not a closed system. It is regularly resupplied by cargo spacecraft from Earth, bringing food, water, spare parts, and new equipment. It relies on Earth for mission control, for medical advice, for troubleshooting support. Water is recycled to a high degree, and oxygen is produced by electrolysis of water, but the system is not closed and cannot function independently of Earth. The ISS also has the advantage of being in Earth orbit only a few hundred kilometers away, reachable in a matter of hours by spacecraft. Mars is millions of kilometers away, reachable only over many months. The ISS demonstrates that humans can survive in space, but it does not demonstrate that humans can colonize another planet. Let us talk about Mars Direct and other mission architectures, because these are often presented as realistic plans for colonization. Mars Direct, proposed by engineer Robert Zubrin, is a minimalist approach that aims to reduce the cost and complexity of a Mars mission by using in situ resource utilization, specifically producing rocket fuel from the Martian atmosphere. The plan involves sending an uncrewed spacecraft to Mars ahead of the crew, carrying a small nuclear reactor and a chemical plant that would produce methane and oxygen from carbon dioxide in the atmosphere and hydrogen brought from Earth. This fuel would be used for the return journey. The crew would launch 2 years later, land near the fuel production site, and spend 18 months on the surface before returning to Earth. Mars Direct is an elegant concept, but it assumes that the technology will work as planned, that nothing will go wrong, that the crew will remain healthy and functional throughout a multi-year mission. It is a plan for a sortie, a brief visit, not for colonization. Establishing a permanent colony would require scaling up every aspect of Mars Direct by orders of magnitude, building not one habitat but dozens, not one fuel production plant, but entire industrial complexes, not supporting a crew of 4 to 6 for 18 months, but supporting a population of thousands indefinitely. The gap between a Mars Direct style mission and actual colonization is vast. Let us consider what would happen if a colony were established and then something went wrong. History provides numerous examples of failed colonies. Roanoke, the lost colony in North America, disappeared without a trace. Jamestown nearly failed due to starvation, disease, and conflict. Many early European settlements in the Americas, in Africa, in Australia, collapsed or barely survived. These colonies had the advantage of being on Earth, with breathable air, liquid water, and at least some local resources to exploit. Mars offers none of these advantages. If a Martian colony were to lose its resupply from Earth, whether due to economic collapse on Earth, political upheaval, war, or simply a loss of interest and funding, the colony would be on its own. The life support systems would eventually fail as components wear out and cannot be replaced. Food production would decline as equipment breaks down. Medical supplies would run out. The population would dwindle through accident, disease, and the failure to reproduce successfully. Within a generation, perhaps 2, the colony would be dead, leaving behind only ruins, a monument to human hubris, a tomb on a distant world. And Earth would not be able to mount a rescue mission because the cost and logistical challenges would be prohibitive, and because by the time anyone on Earth realized that the colony was in trouble, it would likely be too late. There is also the question of contamination, both forward contamination, the risk of introducing Earth life to Mars, and back contamination, the risk of bringing Martian life, if it exists, back to Earth. Forward contamination is a concern because if Earth microbes become established on Mars, they could complicate or even ruin the search for indigenous Martian life, making it impossible to determine whether any life found on Mars is native or was brought by us. This is why planetary protection protocols exist, requiring spacecraft sent to Mars to be sterilized to reduce the number of viable microbes. But a human colony would be a massive source of contamination. Humans carry trillions of microbes on and in our bodies, in our gut, on our skin, in our respiratory tract. These microbes would be shed constantly into the air, onto surfaces, into the waste streams. Some of these microbes might be able to survive on Mars, particularly in the sheltered, relatively warm, and humid environment of a habitat or greenhouse. If they were released into the Martian environment, either accidentally through a breach or deliberately through waste disposal, they could potentially establish themselves in subsurface ice deposits or in transient liquid water, contaminating the planet. This would be an irreversible act, a form of biological pollution that would compromise the scientific value of Mars forever. Back contamination is a more speculative but potentially more serious concern. If Mars harbors life, even microbial life, and if that life were brought back to Earth, either on the bodies of returning astronauts, on their equipment, or in samples, there is a risk that Martian organisms could be harmful to Earth life. This risk is considered low because any Martian life would have evolved independently and would likely not be compatible with Earth biochemistry, but it cannot be entirely ruled out. Prions, the infectious proteins that cause diseases like Creutzfeldt-Jakob disease, remind us that even non-living or quasi-living entities can be pathogenic if they interact with biological systems in unexpected ways. Planetary protection protocols require that samples returned from Mars be handled in strict biological containment, analyzed for signs of life, and subjected to extensive testing before being released. Astronauts returning from Mars would likely need to undergo quarantine, as the Apollo astronauts did upon returning from the Moon, to ensure they are not carrying any Martian organisms. This adds another layer of complexity and cost to any Mars mission, and it raises the question of whether the risks are justified by the potential benefits. Let us think about the children again, because they are the true test of whether a colony can succeed. A colony is not sustainable unless it can reproduce, unless a next generation is born, raised, and can in turn have children of their own. On Mars, as we have discussed, reproduction is uncertain at best, but even if children can be born, can they be raised to become healthy, functional adults? Child development is not merely a biological process, but a psychological and social one. Children need not only physical care, but also emotional support, intellectual stimulation, social interaction, and a sense of belonging to a community and a culture. On Earth, children grow up in a world of immense richness, exposed to nature, to other children, to diverse adults, to books, art, music, and the accumulated knowledge and culture of humanity. On Mars, children would grow up in a confined habitat with only a small number of adults, most of whom would be busy with survival tasks. Education would be limited, likely conducted remotely using materials from Earth, or by the few adults who have teaching skills. Socialization would be limited to the other children in the colony, a small peer group that might number only a handful in the early years. The psychological effects of such an upbringing are unknown, but they would likely be profound. The children of Mars would be shaped by their environment in ways that we cannot fully predict, and it is unclear whether they would develop into the kind of resilient, adaptable, creative individuals that the colony would need to survive and eventually thrive. Then there is the question of identity. Who would the Martian colonists be? Would they see themselves as Martians, as a new branch of humanity distinct from Earth? Or would they see themselves as exiles, as Earthlings stranded on an alien world, forever longing for a home they can never return to? Identity is shaped by many factors, by culture, by history, by environment, by the stories we tell ourselves about who we are and where we belong. The first generation of Martian colonists would have been born on Earth, and they would carry with them the memories, the languages, the cultural references of Earth. But their children would be Martian-born, and their experience would be fundamentally different. They would have no direct memory of Earth, only stories, images, videos. They would grow up in a world where the sky is pink, where you cannot go outside without a suit, where everything is scarce and every resource is precious. They might develop a resentment toward Earth, a feeling that Earth abandoned them, or a feeling of superiority, that they are the pioneers, the vanguard of humanity's future, while Earth is mired in its old problems. This divergence of identity could lead to conflict, both within the colony and between the colony and Earth. It could also lead to a sense of alienation, a feeling of not belonging anywhere, of being caught between two worlds, fully part of neither. Let us consider the parallels with other utopian projects, because the idea of colonizing Mars is, at its heart, a utopian vision. It is the idea that humanity can start fresh, can build a new society free from the mistakes and injustices of Earth, can create a better world on a blank slate. But history teaches us that utopian projects rarely succeed. They're undermined by human nature, by the persistence of old conflicts and hierarchies, by the gap between the ideal and the reality. The American colonies were in some sense a utopian project, a new world where people could escape religious persecution, economic hardship, and the rigid class structures of Europe. But the colonies brought with them slavery, genocide, and inequality. The Soviet Union was founded on utopian ideals of equality and justice, but it devolved into totalitarianism, repression, and economic stagnation. Intentional communities from the Shakers to the various communes of the 1960s have generally either dissolved or transformed into something very different from their original vision. Mars would be no different. The colonists would bring with them their biases, their flaws, their conflicts. The constraints of the environment would impose new hierarchies, new inequalities. Those with critical skills would have power over those without. Those who control the life support systems, the food supply, the communication links, would have power over everyone else. The promise of a new beginning would give way to the same old struggles for power, resources, and recognition. Let us talk about time, because time is a dimension of this problem that is often ignored. The universe is old, approximately 13.8 billion years. The Earth is about 4.5 billion years old. Life on Earth has existed for at least 3.5 billion years, and complex multicellular life for about 600 million years. Humans, anatomically modern humans, have existed for only about 300,000 years, a blink of an eye in geological terms. Civilization, the period during which humans have lived in cities, developed writing, and accumulated technological knowledge spans only about 10,000 years. The industrial age, the period during which we have had the technological capacity to even imagine going to Mars, is only about 250 years old. The space age is less than 70 years old. In the grand sweep of cosmic time, we are newcomers. Our existence is fragile, and our ambitions are often disconnected from the timescales on which planets and stars operate. Mars has been a cold, dry, dead world for billions of years. It will remain so for billions of years to come, barring some intervention that we are nowhere near capable of executing. The window during which humanity exists, during which we have the technology and the resources to even attempt colonization, is likely to be short, a few centuries at most, and possibly much less if we fail to address the existential threats we face on Earth, such as climate change, nuclear war, pandemics, or ecological collapse. If we exhaust ourselves trying to colonize a world that does not want us, we may lack the resources to solve the problems that actually threaten our survival. Let us consider the ethical implications of resource allocation. A human mission to Mars, let alone a colony, would cost hundreds of billions to trillions of dollars. These are resources that could be spent on Earth, addressing problems that cause immense suffering right now. We could use these resources to combat climate change, to transition to renewable energy, to protect and restore ecosystems, to lift people out of poverty, to provide healthcare and education, to fund research into medicine, agriculture, and technology that improves life on Earth. The argument is sometimes made that space exploration inspires people, that it drives technological innovation, that it unites humanity around a common goal. There's some truth to this, but these benefits are diffuse and difficult to quantify, and they must be weighed against the direct, tangible benefits of spending those resources on earthly problems. Moreover, the technological innovations driven by space exploration are often overstated. Many of the technologies attributed to the space program, such as Velcro, Teflon, and Tang, were not actually invented by NASA, and the technologies that were developed for space often have limited applicability on Earth. The real benefit of space exploration is knowledge, the scientific understanding we gain of the universe, and this can be achieved far more cost-effectively with robotic missions than with human missions. Let us examine the role of robotics, because robots have already proven themselves to be extraordinarily capable explorers of Mars. The rover's Spirit, Opportunity, Curiosity, and Perseverance have explored the Martian surface for years, traveling many kilometers, analyzing rocks and soil, searching for signs of past water and past life, and sending back stunning images and invaluable data. These missions have cost a tiny fraction of what a human mission would cost, and they have carried no risk to human life. Robots do not need oxygen, water, or food. They do not suffer from radiation exposure or bone loss. They do not get bored, lonely, or depressed. They can be powered by solar panels or nuclear batteries, and they can operate for years or even decades. Future robots will be even more capable, equipped with artificial intelligence, machine learning, advanced sensors, and dexterous manipulators that allow them to perform complex tasks. They will be able to drill, excavate, analyze, and even assemble structures, all without human supervision, or with supervision provided by operators on Earth despite the communication delay. The argument for sending humans to Mars rather than robots is that humans are more adaptable, more capable of handling the unexpected, and better able to make nuanced judgments in the field. This is true, but the question is whether these advantages are worth the cost and risk. For scientific exploration, the answer is almost certainly no. For colonization, the question is moot, because colonization is not about science. It is about human presence, about the symbolic and psychological significance of humans living on another world, and this is a much weaker justification for the expenditure of resources and the risks involved. Let us return to the question of the atmosphere, because this is the single most defining feature of Mars as an environment. An atmosphere is not merely a layer of gas. It is a system, a dynamic, interconnected web of processes involving pressure, temperature, composition, circulation, and interaction with the surface and with space. Earth's atmosphere is the product of billions of years of geological and biological evolution. It is maintained by the cycling of elements through the biosphere, the hydrosphere, the lithosphere, and the atmosphere itself. The nitrogen cycle, the carbon cycle, the oxygen cycle, the water cycle, these are not just abstract concepts. They are the mechanisms by which Earth remains habitable. Mars has none of these cycles, or only vestigial remnants. Its atmosphere is static, thin, and unresponsive. You cannot breathe it. You cannot use it to generate lift for aircraft without extremely specialized designs. You cannot use it for combustion because there is no oxygen, and you cannot rely on it for thermal regulation because it has almost no heat capacity. When people imagine Mars, they often imagine walking on the surface, feeling the wind on their face, looking up at the sky. But you cannot feel the wind on Mars, not through a spacesuit. The atmospheric pressure is so low that even strong winds, which do occur during dust storms, exert very little force. The wind on Mars is more a movement of particles than a flow of air, and while it can lift dust and obscure the sun, it cannot cool you by convection the way wind does on Earth. The sky is not a comforting presence, but a reminder of absence, of the lack of a thick, protective blanket of air that makes Earth feel like home. Let us think about dust, because Martian dust is not like Earth dust. It is fine, pervasive, abrasive, and electrostatically charged. The dust particles on Mars are smaller on average than those on Earth, often only a few micrometers in diameter, and they have sharp, jagged edges because there is no water to erode and round them. This dust gets into everything. It coats solar panels, reducing their efficiency. It infiltrates seals and joints, causing mechanical wear. It clings to spacesuits and is carried into habitats where it could contaminate the air and pose a health risk if inhaled. Martian dust may contain perchlorates, which are toxic to humans, and the fine particles, if inhaled, could cause respiratory problems, similar to those experienced by miners who inhale silica dust, leading to a condition analogous to silicosis. The Apollo astronauts, despite only brief excursions on the moon, found lunar dust to be a major nuisance and a potential health hazard, and Martian dust would be similar. Managing dust would be a constant battle, requiring airlocks with multiple stages, vacuum cleaning systems, and protocols for decontaminating suits and equipment before entering the habitat. But no system is perfect, and over time, dust would accumulate, both inside and outside, degrading equipment, reducing efficiency, and posing a health risk. Let us address the myth of the pioneer spirit, the idea that the challenges of Mars would bring out the best in humanity, that the hardships would forge a stronger, more resilient people. This is a romantic notion, rooted in frontier mythology and the valorization of pioneers who settled the American West, the Australian outback, the Siberian taiga. But this mythology glosses over the suffering, the failure, the violence, and the exploitation that characterize these frontier societies. Many pioneers died from disease, from starvation, from violence, from accidents. Many settlements failed. Those that succeeded often did so by exploiting indigenous peoples, by extracting resources unsustainably, by creating societies marked by inequality and hardship. The frontier was not a crucible that ennobled people. It was a harsh environment that killed the weak, the unlucky, and the unprepared, and that often brutalized even the survivors. Mars would be even harsher. There's no game to hunt, no land to farm without immense technological input, no indigenous people to displace or trade with, no neighboring settlements to turn to for help. The colonists would be entirely on their own, and the environment would be unforgiving. The pioneer spirit, such as it is, might sustain people for a time, but it would not protect them from the cold equations of biology, physics, and resource scarcity. Let us think about communication in more depth, because the isolation from Earth is not merely physical, but informational and social. Real-time conversation, the natural flow of dialogue, the ability to ask a question and receive an immediate answer, the back and forth of debate, the spontaneity of laughter and shared moments, all of this is impossible when every exchange is delayed by minutes or tens of minutes. Relationships with people on Earth, with family, with friends, would become attenuated, would become one-sided, would shift from dialogue to monologue. You would send a message and then wait. And by the time the response arrived, the moment would have passed. The emotional context would have changed, and the conversation would feel stilted and artificial. Over time, the bonds with Earth would weaken. The people on Mars would form their own tight-knit community, because these are the people you see every day, the people you depend on, the people whose presence is immediate. But this community would be small, insular, and isolated, and the relationships within it would be intense and fraught, because there is no escape, no ability to take a break from someone who annoys you, no opportunity to meet new people and form new connections. The social dynamics would resemble those of a submarine crew or an Antarctic research station, but magnified by the permanence and the knowledge that this is your life forever. Let us consider art and beauty, because these are fundamental human needs, often neglected in technical discussions of colonization. Humans do not live by bread alone. We need beauty, meaning, transcendence, connection to something larger than ourselves. On Earth, we find these things in nature, in the diversity of landscapes, in the play of light on water, in forests and mountains and deserts and oceans. We find them in art, in music, in literature, in architecture, in the cultural expressions of diverse societies. On Mars, nature is alien and barren. There are no forests, no oceans, no life except what we bring with us. The landscape, while it has a stark beauty, is monotonous, unchanging, dead. The sky is a wrong color. The sunlight is dim. The stars, though brilliant, are cold and distant. Art on Mars would have to be created by the colonists themselves, from limited materials and with limited time, because survival takes precedence over creation. Music could be recorded and brought from Earth, but live performance would be rare, limited to whatever instruments can be transported and whatever talent exists within the small population. Literature could be written, but the experiences that inspired literature on Mars would be narrow, repetitive, focused on the daily struggle to survive. The great themes of human literature, love, loss, longing, conflict, redemption, would still be present, but they would be played out against a backdrop of confinement and scarcity, and the resulting works might be bleak, introspective, and tragic rather than uplifting or inspiring. Let us talk about religion and spirituality, because for many humans, these are sources of meaning and comfort. How would religious and spiritual life manifest on Mars? Some colonists would bring their faith with them, and they would practice it as best they could, but religious practice often involves community, ritual, sacred spaces, and connection to tradition and a history that are rooted in earth. A mosque, a church, a temple, a synagogue on Mars would be a pale imitation of its earthly counterpart. A room in a habitat where a small group gathers to pray or meditate or celebrate. Pilgrimages, a central practice in many religions, would be impossible. Holy sites are on Earth, not on Mars. If the founding population is small, and if the colony remains isolated, genetic diversity would decline, and heritable disorders would become more common. Managing this would require either periodic influxes of new colonists from Earth, which would be expensive and difficult, or the use of advanced reproductive technologies such as genetic screening, gene editing, or the use of frozen gametes and embryos from Earth, which raises a host of ethical and practical questions. Let us address the question of motivation again, but from the perspective of the children. Why would the second and third generations continue to maintain the colony? They did not choose to be born on Mars. They have no loyalty to the vision that brought the first colonists there. Their life is one of hardship and deprivation, and they might reasonably question whether it is worth continuing. On Earth, societies are held together by a complex mix of shared culture, economic interdependence, coercion by the state, and the simple fact that there is nowhere else to go. On Mars, the colonies held together by the necessities of survival, by the fact that everyone depends on everyone else, and by the absence of any alternative. But what if individuals or groups decide that they no longer want to participate? What if they refuse to do their share of the work? Or if they sabotage systems? Or if they simply give up? In a small, fragile colony, the defection or rebellion of even a few individuals could threaten the survival of everyone. Maintaining social cohesion would require not only effective governance and fair distribution of resources, but also a sense of shared purpose and meaning. But what is the purpose of a Martian colony? Is it survival for its own sake, continuing to exist simply because you're already there? Is it the hope that someday, perhaps centuries in the future, Mars will be transformed into a habitable world? Is it the belief that you are the vanguard of humanity's expansion into the cosmos, pioneers paving the way for future generations? These narratives might sustain the first generation, but they might ring hollow to later generations who bear the costs without seeing the benefits. Let us consider the possibility of failure in detail, because failure is a real and perhaps likely outcome. What would failure look like? It might be sudden, a catastrophic systems failure that kills everyone in the colony within hours or days, a breach in the habitat hull, a failure of the oxygen generation system, an explosion, a fire, a catastrophic medical emergency. Or it might be gradual, a slow decline as equipment wears out, as resources dwindle, as the population shrinks due to accidents, illness, low birth rates, or emigration if return to Earth is possible. The colony might experience a crisis, a crop failure, an epidemic, a civil conflict that it cannot recover from. The survivors might limp along for years, scavenging from the remnants of the infrastructure, living in increasingly desperate conditions until finally the last person dies. Or the colony might be abandoned, with the colonists, if they are able, returning to Earth or being evacuated, leaving behind the habitats and equipment as monuments to a failed dream. History is littered with failed colonies, from Roanoke to countless others that are now forgotten, and there is no reason to believe that a Martian colony would be immune to the same fate. Let us think about the ethics of failure. If a Martian colony fails and people die, who is responsible? The company or government that organized the mission? The engineers who designed the systems? The colonists themselves for accepting the risks? If the colony is abandoned and the colonists return to Earth, if that is even possible, they would face a world that has moved on without them, where they would be anachronisms, exiles returning from a failed dream, bearing the physical and psychological scars of their experience. They would face the challenge of reintegrating into earthly society, of relearning how to live in one gravity, of reconnecting with family and friends who have aged and changed in their absence. Many might find that they no longer fit in, that they are caught between two worlds, belonging to neither. And if the colony fails and no one returns, if everyone dies, then the only legacy would be the silent habitats, the empty rooms, the machines slowly running down, a tomb on a distant world, a monument to human hubris. Let us ask ourselves what we are really seeking when we talk about colonizing Mars. Are we seeking survival, a backup for humanity in case Earth becomes uninhabitable? If so, the logic is flawed, because making Earth uninhabitable would require catastrophes so severe that Mars, which is already uninhabitable, would offer no refuge. The rituals might continue, but they would be divorced from the landscapes, the histories, the communities that give them full meaning. For some, this disconnection would be deeply painful, a spiritual exile to accompany the physical one. Others might develop new forms of spirituality, adapted to the Martian environment, perhaps venerating Mars itself, or the sun, or the act of survival and creation in a hostile world. But these new forms would lack the depth and richness of traditions that have evolved over millennia, and they might feel hollow or artificial to many. Let us examine the concept of sustainability, because for a Martian colony to be truly independent, it must be sustainable, meaning that it can maintain itself indefinitely without input from Earth. Sustainability involves closing the loops of resource use so that waste products are recycled into inputs and so that the system can continue indefinitely. On Earth, the biosphere is sustainable because it is powered by sunlight, because it has vast reservoirs of elements and compounds that are cycled through living organisms and the environment, and because it has evolved over billions of years to be robust and resilient. A Martian colony would be attempting to create from scratch a much smaller and less robust system, and to make it sustainable within a human timescale, which is to say within decades or at most a few centuries. The challenges are immense. Every element needed for life and industry, carbon, nitrogen, oxygen, hydrogen, phosphorus, sulfur, metals, must be sourced from Mars, extracted, purified, and incorporated into the colony's systems. Some of these elements, like iron, are abundant on Mars. Others, like nitrogen, are scarce. Nitrogen is essential for amino acids, proteins, DNA, and RNA, and it is also needed in large quantities for agriculture to synthesize fertilizers. Mars's atmosphere contains some nitrogen, but extracting it from the thin air would be energy intensive. Some nitrogen might be locked in nitrate salts in the regolith, but mining and processing these would also require significant effort. And if the colony cannot close the nitrogen loop, it would need to import nitrogen from Earth or from elsewhere in the solar system, which defeats the purpose of sustainability. Phosphorus is another critical element essential for DNA, RNA, and ATP, the energy currency of cells. It is also a key component of fertilizers. Phosphorus must be mined from rocks, and while Mars likely has phosphorus-bearing minerals, finding concentrated deposits, mining them, and extracting the phosphorus would be challenging. On Earth, phosphorus is being depleted from soils and is becoming a limiting factor in agriculture. And this problem would be even more acute on Mars, where there are no natural phosphorus cycles and where every atom of phosphorus would have to be carefully managed and recycled. Then there are the trace elements, the vitamins, the micronutrients that life depends on. Humans need iodine for thyroid function, selenium for enzyme activity, zinc, copper, iron, and many others in small amounts. Plants need similar micronutrients. If the Martian regolith is deficient in any of these, the colony would need to import them or synthesize them, which may not be possible. The web of dependencies is intricate and fragile, and breaking any single link could cause the system to fail. Let us think about energy again, but in more detail. Energy is the foundation of everything. Without energy, you cannot produce oxygen, recycle water, grow food, maintain temperature, run computers, or power equipment. On Earth, we have had the luxury of cheap, abundant energy from fossil fuels, and more recently, from renewable sources. On Mars, energy would be expensive and limited. Solar power is the most obvious choice, but as we've discussed, it is less efficient on Mars, and dust storms can block the sun for extended periods. During a major dust storm, which can last for weeks and even months, solar panels would produce almost no power, and the colony would have to rely on stored energy in batteries or other storage systems. Batteries have limited capacity and limited lifespans, and maintaining a storage system large enough to carry the colony through a prolonged dust storm would be a significant challenge. Nuclear power is more reliable, but it requires fuel, either uranium or plutonium, which would have to be brought from Earth or mined and enriched on Mars, both of which are complex and dangerous processes. A nuclear reactor also requires cooling, which is difficult on Mars because there is no large body of water to act as a heat sink, and because the thin atmosphere makes convective cooling inefficient. Waste heat would have to be radiated to space using large radiator panels, which are vulnerable to dust accumulation and damage. And if the reactor fails, if there is a meltdown or a leak of radioactive material, the consequences for the small, confined colony would be catastrophic. Let us consider materials and manufacturing, because a self-sustaining colony must be able to produce its own tools, spare parts, and infrastructure. This requires mining, smelting, refining, and fabrication. Mars has rock and metal, but turning these raw materials into useful products is not straightforward. On Earth, we have centuries of accumulated knowledge and technology for extracting and processing materials, and we have vast industrial infrastructure. On Mars, you would be starting from scratch with limited equipment and limited expertise. Mining on Mars would involve digging or drilling into regolith or rock, which is easier than on Earth in some respects due to the lower gravity, but harder in others due to the lack of atmospheric pressure to help with certain extraction techniques. Smelting, the process of heating ore to extract metal, requires high temperatures, which require energy. Refining metals to the purity needed for electronics or precision machinery requires chemical processes, many of which use reagents that would have to be synthesized on Mars from available materials. Fabrication, turning metal and other materials into parts, requires machine tools, such as lathes, milling machines, and 3D printers. These tools themselves are complex and require maintenance and eventual replacement. Bootstrapping an industrial capacity on Mars would be a multi-generational project, and in the meantime, the colony would be dependent on spare parts and equipment brought from Earth. Let us talk about information technology, because a Martian colony would depend heavily on computers, software, sensors, and communication systems. These technologies are fragile and degrade over time. Computers fail, hard drives crash. Software has bugs. Sensors drift out of calibration. On Earth, these are minor inconveniences because we can easily obtain replacements, repairs, and updates. On Mars, every piece of hardware would be precious, and every failure would be a crisis. The colony would need to carry extensive redundancy, multiple backups of every critical system, and it would need personnel with the skills to repair and maintain computers, to write and debug software, to design and build electronic circuits. But the environment on Mars is hostile to electronics. Radiation can cause bit flips in memory and processors, leading to computational errors or crashes. Dust can infiltrate connectors and cooling systems. Temperature swings can cause solder joints to crack and components to fail. The colony's computers would need to be hardened against these threats, which increases their cost and complexity, and even then, failures would occur. Data storage is another concern. Digital data degrades over time, especially on magnetic and flash media. The colony would need to maintain archives of essential information, including scientific knowledge, engineering designs, agricultural data, medical references, and cultural records. And these archives would need to be stored on multiple media, regularly checked for integrity, and migrated to new storage systems as old ones fail. If the colony loses its data, it loses its knowledge, and it would be set back potentially decades. Let us examine the legal and political dimensions more closely. As mentioned earlier, the Outer Space Treaty of 1967 states that celestial bodies are the common heritage of mankind and that no nation can claim sovereignty over them. This treaty has been signed by most spacefaring nations, but it is unclear how it would apply to a Martian colony, especially one established by a private corporation. Can a company own land on Mars? Can it own the resources it extracts? Can it govern the people who live there? These questions have not been definitively answered, and they will become pressing once a colony is actually established. There's also the question of jurisdiction. If a crime is committed on Mars, under what legal system is it prosecuted? If a dispute arises between colonists, how is it resolved? If the colony declares independence from Earth, would Earth recognize it? Would trade be possible? And under what terms? Would Earth have any leverage to enforce its will? Or would Mars be a de facto independent state from the outset? The history of colonies on Earth suggests that these issues would be contentious and could lead to conflict. The American Revolution was fought over issues of taxation and representation. Many other independence movements have been violent and protracted. Mars would have the advantage of distance, which makes military intervention from Earth impractical, but it also has a disadvantage of dependence because in the early stages, the colony would rely on Earth for supplies and support. This asymmetry of power could be exploited, with Earth using the threat of cutting off supplies to maintain control, or with the colony using the threat of default on debts or refusal to cooperate to assert its autonomy. The political relationship between Earth and a Martian colony would be fraught and would likely evolve over time as the colony becomes more self-sufficient and as its interests diverge from those of Earth. Let us think about what happens if multiple colonies are established by different nations or corporations. Would they cooperate or compete? On Earth, human history is marked by competition for resources, by conflict, and by war. There is no reason to think that Mars would be different. If one colony finds a rich deposit of water ice or valuable minerals, would other colonies respect its claim, or would they attempt to seize it? If resources are scarce, as they certainly would be in the early stages, competition could turn violent. And unlike on Earth, where there are laws, treaties, international organizations, and at least some mechanisms for resolving disputes, Mars would have none of these, at least initially. The colonies would be isolated from each other, unable to project force over large distances due to the difficulty of travel on Mars, but also unable to communicate easily or to build trust. The result could be a fragmented, balkanized Mars, with each colony an isolated polity, suspicious of its neighbors, hoarding resources, and preparing for conflict. Alternatively, if one colony or one corporation becomes dominant, it could establish a monopoly, controlling access to key resources and infrastructure, and imposing its will on others. This would be a form of colonialism, but with the colonizers and the colonized all being of earthly origin, separated only by their allegiance to different entities. Let us return to the human body and explore some of the more subtle physiological effects of living on Mars. The immune system, as we've touched upon, would be compromised, but the mechanisms are worth exploring in more detail. The thymus, an organ located in the chest that is responsible for maturing T cells, a type of white blood cell critical for adaptive immunity, atrophies in microgravity. Studies on astronauts have shown reduced thymus size and altered T cell populations after spaceflight. On Mars, with partial gravity, the effect might be less severe, but it would still be present. This means that the body's ability to respond to new infections, to develop immunity to new pathogens, and to maintain surveillance against cancer cells would be impaired. Wound healing, which relies on the immune system to prevent infection and to coordinate the repair process, would be slower, and infections would be more likely to become serious. The gut microbiome, the community of trillions of bacteria that live in the digestive tract and play critical roles in digestion, vitamin synthesis, and immune function, would also be affected. Studies have shown that the gut microbiome changes in space, with certain beneficial species declining and potentially harmful species increasing. On Mars, the diet would be different from Earth diets, the environment would be different, and the stress would be different, all of which would affect the microbiome. If the microbiome becomes unbalanced, it could lead to gastrointestinal problems, nutritional deficiencies, and increased susceptibility to disease. Maintaining a healthy microbiome would require careful attention to diet, possibly supplementation with probiotics, and monitoring of the microbial community, but these measures might not be sufficient given the multiple stresses acting on the colonists. Let us consider the cardiovascular system in more detail. The heart is a muscle, and like all muscles, it adapts to the demands placed on it. In microgravity, the heart does not have to pump as hard to circulate blood, and it becomes smaller and weaker. On Mars, the heart would face an intermediate demand, more than in microgravity, but less than on Earth. Over time, the heart would adapt to this new equilibrium, but the question is whether this adapted heart would be healthy or whether it would be prone to dysfunction. On Earth, cardiovascular fitness is maintained by regular exercise, by activities that challenge the heart and make it work harder. On Mars, even with exercise, the reduced gravity would mean that the heart never experiences the same level of challenge as it does on Earth. The result could be a form of deconditioning, a gradual weakening of the cardiovascular system that would make colonists more susceptible to heart disease, arrhythmias, and heart failure. And if a colonist were to return to Earth, the heart, now adapted to Martian gravity, might be unable to cope with the increased demands of Earth gravity, leading to acute cardiovascular distress, potentially even heart failure or stroke. The blood itself might also be affected. Erythropoiesis, the production of red blood cells, is regulated by the kidneys in response to oxygen levels. In microgravity, astronauts experience a reduction in red blood cell mass because the body perceives that less oxygen carrying capacity is needed. On Mars, with lower atmospheric pressure and lower levels of physical exertion due to reduced gravity, a similar reduction might occur. Fewer red blood cells means less oxygen delivery to tissues, which could cause fatigue, weakness, and reduce physical and cognitive performance. Anemia, a condition of insufficient red blood cells, could become common, especially given the stresses of radiation, poor diet, and potential vitamin and mineral deficiencies. Treating anemia would require iron supplementation, vitamin B12, folate, and possibly erythropoietin injections, but these resources might be limited, and the underlying causes, the environmental stresses, would persist. Let us think about the psychological concept of place attachment, the emotional bond between people and the places they live. On Earth, people develop deep attachments to their homes, their neighborhoods, their regions, their countries. These attachments are formed through experience, through memories, through the sensory and emotional associations with a place. Place attachment provides a sense of identity, belonging, and rootedness. It is a source of comfort and stability. On Mars, place attachment would be complicated. The habitat is not a natural place. It is a machine, a life support system, a shelter against a hostile environment. It lacks the richness, the variety, the history that make earthly places feel like home. The Martian landscape, while it might inspire awe, is alien and inhospitable, not a place where you can walk freely, sit on the ground, feel the sun on your skin, or breathe the air. The colonists might develop an attachment to the habitat, to the small community they live in, to the routines and rituals of daily life. But this attachment would be tinged with ambivalence, with the knowledge that this is not home, not in the deep, instinctive sense, but rather a place of exile, a place you are stuck. This ambivalence could manifest as a chronic, low-level distress, a sense of unease or displacement that never fully goes away, even as years pass and the habitat becomes familiar. Let us consider the sensory environment because humans are sensory beings and our well-being depends in part on the richness and variety of sensory input. On Earth, we are constantly receiving a flood of sensory information, sights, sounds, smells, textures, tastes. The environment is complex and ever-changing with weather, seasons, day and night cycles, the presence of plants and animals, the textures of natural and built environments. On Mars, sensory input would be impoverished. Inside the habitat, the environment would be controlled, monotonous, dominated by artificial lighting, recycled air, and synthetic materials. There would be few smells because most of the materials in the habitat would be chosen for being inert and non-outgassing, and because the air filtration system would remove odors. There would be few sounds because the habitat would be well insulated and because there are few sources of noise beyond the hum of ventilation and the occasional beep of equipment. The visual environment would lack natural light, lacking the full spectrum and the dynamic variation of sunlight on Earth. Artificial lights can approximate sunlight, but they are not the same, and prolonged exposure to artificial light is associated with mood disorders, sleep disturbances, and eye strain. Outside the habitat, the environment is visually stark, orally silent, and texturally uniform, dominated by dust and rock. The lack of sensory richness could lead to a kind of sensory deprivation, contributing to boredom, depression, and cognitive decline. Let us discuss the issue of time perception and circadian rhythms. Humans have an internal biological clock, the circadian rhythm, that regulates sleep-wake cycles, hormone production, metabolism, and many other physiological processes. This clock is entrained or synchronized to the 24-hour day-night cycle of Earth by exposure to natural light, particularly the blue wavelengths present in sunlight. On Mars, the day, called a sol, is approximately 24 hours and 39 minutes long, only slightly longer than an Earth day. This small difference might not seem significant, but studies have shown that even small mismatches between the circadian rhythm and the environmental light-dark cycle can lead to sleep disturbances, fatigue, mood disorders, and impaired cognitive performance. The colonists would likely use artificial lighting to create a day-night cycle synchronized to the Martian sol. But whether the human circadian clock can fully adapt to a 24.6-hour cycle is uncertain. Some individuals might adapt easily, while others might experience chronic circadian misalignment, similar to perpetual jet lag. This misalignment would be exacerbated by the lack of natural sunlight because the artificial lights in the habitat, even if they are full spectrum, would not have the same intensity or the same spectral qualities as sunlight, and the colonists would be indoors most of the time with little exposure to the limited natural light available on Mars. Over time, this could lead to a condition known as seasonal affective disorder, or SAD, a type of depression associated with insufficient light exposure, commonly experienced in polar regions of Earth during the winter months when the sun is below the horizon for extended periods. Let us examine the concept of psychological resilience, the ability to cope with stress, to adapt to adversity, and to recover from trauma. Resilience is not a fixed trait. It is influenced by many factors, including genetics, early life experiences, social support, coping skills, and environmental conditions. On Mars, the stresses would be chronic and multifaceted, testing resilience in ways that few environments on Earth do. Some individuals would be highly resilient, able to adapt, to find meaning in the challenge, to maintain optimism despite the hardships. But resilience has limits. Even the most resilient person can be worn down by unrelenting stress, by repeated setbacks, by the absence of relief, or reprieve. On Earth, when we face stress, we can take a vacation, we can escape to nature, we can seek support from a wide network of friends and family, we can access professional mental health services. On Mars, these coping mechanisms would be limited or absent. There is no vacation from Mars. There is no nature to escape to. The social network is small and is itself under stress. Mental health services would be minimal. The result would be that even initially resilient individuals might experience psychological breakdown after years of living in such an environment, and the rate of mental health problems would be high. Let us think about the concept of agency, the sense of control over one's life, the ability to make choices and to direct one's own path. Agency is a fundamental human need, closely linked to well-being and mental health. On Mars, agency would be severely constrained. The colonists would be bound by the limits of the habitat, the limits of the life support systems, the limits of available resources. Their daily routines would be dictated by necessity, by the requirements of maintenance and survival. Their long-term future would be uncertain and largely out of their hands, dependent on decisions made by people on Earth, on the continued flow of supplies, on the success or failure of technologies and systems they have limited ability to control. The sense of being trapped, of having no real choices, of being a cog in a machine rather than an autonomous individual would be corrosive to the sense of self and to psychological health. This is a recognized problem in total institutions, places like prisons, psychiatric hospitals, and military barracks, where individuals have little control over their environment and their activities. Mars would be, in many respects, a total institution, and the psychological dynamics would be similar. Let us consider the historical analogy of Antarctic research stations more carefully, because these are perhaps the closest earthly parallel to a Martian colony. Stations like McMurdo, Amundsen Scott at the South Pole, and Concordia are isolated, harsh environments where small groups of people live for extended periods. The winter overcrews, in particular, experience conditions similar to what might be expected on Mars: extreme cold, isolation, confinement, lack of natural light during the polar winter, and limited communication with the outside world. Studies of these populations have revealed a range of psychological and physiological effects. The third quarter phenomenon, a dip in mood and motivation, roughly 3/4 through the winter, is well documented. Interpersonal conflicts increase. Sleep disturbances are common. Some individuals experience subsyndromal depression, a mild but persistent low mood that does not rise to the level of clinical depression, but that still impairs quality of life. There have been instances of more serious psychological crises, including acute psychosis and suicide. And this is in an environment that, while harsh, is still on Earth, where rescue is possible, where the air is breathable, where the gravity is normal, and where the mission is time limited. On Mars, all of these stresses would be amplified, and the knowledge that there is no early escape, that this is permanent, would add an existential weight that Antarctic winter overcrews do not experience. Let us examine the issue of boredom in more depth, because boredom is not a trivial problem. It is a psychological state characterized by a lack of engagement, a sense that nothing is meaningful or interesting, and a restless desire for novelty. Boredom is associated with a range of negative outcomes, including depression, anxiety, substance abuse, and risk-taking behavior. On Mars, the environment would offer little novelty. The tasks would be repetitive, the scenery unchanging, the social interactions limited to the same small group of people. Entertainment would be limited to whatever can be brought from Earth or transmitted, subject to the communication delays. There would be no concerts to attend, no sports events, no festivals, no spontaneous gatherings, no surprise encounters with new people or new places. The colonists would be living in a state of chronic understimulation, and this could lead to a deep and pervasive boredom that is difficult to alleviate. Some individuals might respond by becoming apathetic, going through the motions of daily life without engagement or enthusiasm. Others might seek stimulation through risky behavior, through conflict with others, or through substance use if any psychoactive substances are available. Managing boredom would require intentional efforts to create variety, to encourage hobbies and creative pursuits, to rotate roles and responsibilities, but the limits of the environment would make this difficult, and for some individuals, no amount of intentional variety would be enough. Now let us consider the children again, but from a different angle. What kind of education would they receive? On Earth, education is not merely the transmission of information, but the development of the whole person: cognitive, emotional, social, physical, and moral. Children learn through play, through exploration, through interaction with the environment and with other people, through exposure to art, music, literature, history, science, and diverse perspectives. They learn to navigate complex social situations, to resolve conflicts, to cooperate and compete, to form friendships and alliances. They learn physical skills through sports and outdoor activities. They develop a sense of morality through stories, through examples set by adults, through experiencing consequences of their actions. On Mars, much of this would be missing or attenuated. Play would be constrained by the small, confined space of the habitat. Exploration of the outdoors would be rare and would require spacesuits, turning it into a supervised, technical activity rather than a spontaneous adventure. Social interactions would be limited to a very small peer group. Physical activities would be constrained by the low gravity and the limited space for sports or exercise. Exposure to art, music, and literature would be limited to what can be accessed remotely or to what is created locally by a small number of people. The educational curriculum would likely be functional, focused on the technical skills needed to maintain the colony at the expense of the humanities, the arts, and the broad liberal education that is considered essential for developing well-rounded individuals on Earth. The result would be children who are technically competent, but culturally and intellectually impoverished, who lack the breadth of knowledge and experience that characterizes an educated person, and who might struggle to think critically, to appreciate beauty, to understand history and context, or to engage with complex moral and philosophical questions. Let us think about what happens over multiple generations, because a true colony must be multi-generational. The first generation, the colonists who come from Earth, would carry with them the memory of Earth, the cultural knowledge, the skills, the values of earthly civilization. They would be the link between Earth and Mars. But as they age and die, this link would weaken. The second generation, born on Mars, would have no direct experience of Earth. Their understanding of Earth would be secondhand, based on stories, images, and communications. They might idealize Earth, imagining it as a lost paradise, or they might resent it, seeing it as the place that condemned their parents to exile. The third generation would be even more removed, with Earth becoming a distant, almost mythical place, and Martian culture beginning to solidify into its own distinct form. But this culture would be impoverished, limited by the smallness of the founding population, by the scarcity of resources, by the lack of contact with the broader human civilization. Cultural evolution requires diversity, exchange, and a large population. A small, isolated colony would experience cultural drift and possibly cultural stagnation, with traditions and knowledge being lost over time if they are not carefully preserved. There's also the risk of genetic drift and inbreeding, which we have mentioned, but which becomes more acute over multiple generations. A nuclear war, a runaway greenhouse effect, a pandemic, an asteroid impact, these would be devastating on Earth, but they would not make Earth as hostile as Mars already is. Even a post-apocalyptic Earth, with its ruins and its radiation and its collapsed ecosystems, would still have breathable air, liquid water, and a gravity field that human bodies are adapted to. It would be a better place to survive than Mars. Are we seeking resources? As we've discussed, Mars has no resources that we need and cannot obtain more easily elsewhere. Are we seeking knowledge? We can gain knowledge of Mars more effectively with robotic missions than with human missions. Are we seeking glory, the prestige of being the first, of planting the flag, of achieving what has never been done? This is perhaps the most honest motivation, but it is also the most selfish because it prioritizes the satisfaction of a few individuals or the pride of a nation or a corporation over the welfare of the people who would be sent to Mars and the allocation of resources that could address real needs on Earth. Perhaps what we are really seeking is escape, a way out of the problems we face on Earth, the environmental degradation, the political dysfunction, the social inequality, the sense that things are getting worse and that there is no solution. Mars offers the fantasy of a fresh start, a blank slate, a place where we can leave our mistakes behind and build something better. But this is a fantasy. We cannot escape from ourselves. We bring our problems with us, our biases, our conflicts, our limitations. Mars would not make us better people. It would test us, stress us, amplify our flaws, and likely break us. The real solution to Earth's problems is to address them here, on Earth, where we have the resources, the infrastructure, the knowledge, and the billions of people who can contribute. Investing in sustainability, in renewable energy, in conservation, in social justice, in education, in science, in the arts, in building resilient and equitable societies. These are the ways to ensure humanity's future, not by fleeing to a dead planet in the hope that we can make it live. And yet the dream persists because it is a powerful dream rooted in the human spirit, in our desire to explore, to overcome challenges, to reach beyond our grasp. It is a dream that has inspired art, literature, and science fiction for more than a century. From H.G. Wells's War of the Worlds, to Ray Bradbury's The Martian Chronicles, to Kim Stanley Robinson's Mars trilogy, these stories imagine Mars as a place of adventure, of discovery, of transformation, and they tap into deep currents of myth and aspiration. But they are fiction. They are not blueprints for reality. The real Mars, the Mars revealed by our spacecraft and rovers, is not a place of adventure, but a place of death. A frozen desert where nothing lives and nothing grows, where the air is poison and the ground is toxic, where radiation sleeps slowly into your bones and gravity pulls at your muscles and heart with just enough force to remind you that you are not home, but not enough to keep you strong. It is a world that has no interest in us, that does not want us, that will kill us if we give it the chance. The human body is not designed for Mars. The human mind is not designed for Mars. Our societies, our cultures, our technologies, all of these are products of Earth, adapted to Earth, dependent on Earth. We are Earthlings, and Earth is our home, the only home we've ever known, the only home we will ever truly have. We can visit Mars, perhaps. We can send robots to explore it, to study it, to learn from it. We can dream about it, imagine it, write stories about it, but we cannot live there, not in any meaningful sense, not as thriving, flourishing human beings. We can survive there, barely, for a time, in sealed habitats, at enormous cost, with great suffering, but survival is not life. Life is connection to other people, to the natural world, to the cycles of seasons, to the richness of culture and history. Life is breathing deeply, feeling the wind on your face, walking barefoot on grass, watching clouds drift across a blue sky, hearing the laughter of children playing outside, tasting fresh fruit, smelling rain. None of this exists on Mars. None of this can exist on Mars, not for millennia, if ever. We've explored the atmosphere, the temperature, the gravity, the radiation, the psychological stresses, the physiological adaptations, the challenges of reproduction and child rearing, the difficulties of building and maintaining habitats, the scarcity of resources, the fragility of closed-loop life support, the isolation from Earth, the impoverishment of the sensory and cultural environment, the risks of disease and injury, the problems of governance and social cohesion, the lack of economic viability, the timescales required for any form of terraforming, the lessons from historical analogs, the ethical questions of resource allocation, and the treatment of those who would be sent to Mars. We've considered all of these from multiple angles, revisiting and deepening our understanding with each pass. And at every turn, the conclusion is the same. Mars is not a world for humans. It is not a frontier to be settled, not a refuge to escape to, not a destiny to fulfill. It is a barren rock in space, a beautiful and fascinating world in its own right, worthy of study and respect, but not a home, not a place where we can transplant ourselves and expect to thrive. The real frontier is here, on Earth. The real challenge is to live sustainably on the planet that gave us life, to repair the damage we have done, to build societies that are just and resilient, to care for the biosphere that sustains us, to extend the flourishing that civilization has brought to some people, to all people, to reach a state of equilibrium with our environment so that humanity can continue for not just centuries, but millennia, not as exiles on a hostile world, but as native inhabitants of a world that is, despite all our flaws and failures, still kind to us, still abundant, still beautiful. This is the challenge of our time, and it is a far more important and more achievable challenge than trying to colonize Mars. Mars will still be there. It has been there for 4.5 billion years, and it will be there for billions more. It is patient. It will wait. If, centuries from now, we have solved our problems on Earth, if we have achieved sustainability and prosperity and wisdom, if we have developed technologies that we can barely imagine today, technologies that make the challenges we have discussed tractable or even trivial, then perhaps at that distant time, we might revisit the question of Mars. But that time is not now. Now is the time to focus on Earth, to cherish it, to protect it, to build a future here, because Earth is not a prison we need to escape from. It is a gift, the only gift of its kind in the entire observable universe, a world teeming with life, a world that has given rise to consciousness and culture and love and beauty, a world that for all its troubles is still and will always be our home. The story of Mars and humanity is not a story of colonization. It is a story of exploration, of learning, of coming to understand our place in the cosmos, and of recognizing the preciousness and fragility of the world we inhabit. The robots we send to Mars send back not an invitation, but a warning, a reminder that life is rare, that habitability is a delicate and contingent thing, and that we should not take for granted the extraordinary good fortune of being born on a planet where the air is free and the water flows and the sun warms but does not burn. This is a true lesson of Mars, and it is a lesson we would do well to heed.